Hello my friends and welcome back to the You Can Do TV channel. Producing a machined steel block involves a series of intricate processes that require precision, expertise, and state-of-the-art machinery. In this narrative, we'll delve into the detailed journey of crafting a solid steel block as described in the provided information. The production of a machined steel block begins with the foundational process of open die forging. In this phase, the raw steel material is heated to a high temperature and shaped under tremendous pressure using forging presses. Von Scheuen, equipped with 3 CNC open die forging presses ranging from 7 to 30 meganewtons pressing force, specializes in producing open die forgings and forged bars made of various steel alloys. This initial forging phase ensures the desired structure and properties are imparted to the steel, setting the stage for subsequent processing. After forging, the steel block undergoes preparation before oxy-fuel burning, a crucial step in achieving the final dimensions and specifications. This preparation phase involves meticulous planning and measurement to ensure precise execution during the cutting process. Using advanced oxy-fuel cutting techniques, the steel block is pierced with a hole utilizing an oxygen lance. This initial piercing allows for the subsequent burning of the hole to the required diameter and thickness using the oxy-fuel cutting process. This process showcases the technical capabilities available in oxy-fuel cutting, demonstrating von Scheuen's expertise in handling large-scale steel fabrication. Following the piercing and burning of the hole, attention turns to shaping the outer contour of the steel block. With dimensions of 1000 by 1000 by 1200 millimeters and a thickness of 1200 millimeters, this step demands precision and accuracy. Utilizing CNC flame cutting machines, von Scheuen ensures efficient and precise cutting of the outer contour, even for large dimensions, with up to 6 burners operating simultaneously. The production process continues with the burning of the cone, adding depth to the steel block. This step further demonstrates the versatility of oxy-fuel cutting, allowing for the creation of complex geometries with ease and precision. Quality assurance is paramount throughout the production process. Von Schoen conducts rigorous testing in its own laboratory, including notched bar impact bending tests, KBZ, and tensile tests, to ensure the structural integrity and mechanical properties of the steel block meet the highest standards. After testing, the outer contour undergoes milling for final refinement. This step ensures the surface finish meets the required specifications, enhancing the overall quality and aesthetics of the machined steel block. Von Schoen's capabilities extend beyond the production of machined steel blocks. With expertise in flame cutting, forging, and heat treatment processes, the company offers a comprehensive range of services tailored to meet diverse customer needs. Whether it's flat products cut to precise dimensions or forged components crafted to exact specifications, Von Schoen prides itself on delivering quality products and services. The production process at the PAMA factory is a testament to precision, efficiency, and technological excellence. With a strong tradition dating back to its establishment in 1926, PAMA has become renowned worldwide for its beautiful Italian machine tools catering to serious milling, boring, and drilling needs. Situated in the Trentino region at the heart of the Alps, PAMA benefits from modern transport infrastructure, making it easily accessible by train, car, or plane. The city of Rovereto, rich in historic landmarks, is home to PAMA's main production plants, which are equipped with highly qualified technical teams boasting years of collective experience. PAMA's integrated company structure revolves around two production plants in Rovereto and Brasilia. Here, in their technical departments, all products and components are meticulously developed and manufactured. The main structures are machined in-house using PAMA's own boring, milling machines, and machining centers. The production activities are organized in specialized areas dedicated to building functionally complete modules. These modules undergo rigorous quality control tests at various machining stages to ensure precision and reliability. PAMA's commitment to quality is underscored by its ISO 9001-2008 certification and a vision of constant process and quality improvement. Once the modules pass the stringent tests, they are assembled in the final assembly areas. PAMA's product range includes speed ram floor-type boring and milling machines, speed mat boring and milling centers, speed center horizontal machining centers, and veer ram gantry-type vertical machining centers. Each product boasts unique features tailored to meet specific machining needs. For instance, the speed ram machines are designed for maximum rigidity and stability, while the speed mat centers offer high spindle power and torque. Similarly, the speed center and veer ram machines feature high workpiece swing diameters and integral hydrostatic guideways for enhanced performance. PAMA not only provides cutting-edge machinery but also offers turnkey solutions to meet customers' production requirements. This includes system layout assistance, technological analysis, and training for system programming, use, and maintenance. Furthermore, PAMA's customer care service ensures production efficiency over the years by providing spare parts, service calls, and remote diagnostic systems.
Steel enters Kilsteel's forging hall as solid ingots, ready to be transformed. The first step is upsetting, compressing the stock's length and increasing its diameter. Upsetting concentrates material, where the part needs strength, preparing it for precise shaping. Next, punching creates a central hole, forming a donut shape for seamless rolled ring forging. The punch moves at high speed yet aligns perfectly with the center mark. Seeing a solid ingot change into a ring highlights how force and design meet, though the energy behind each hammer is immense. Hydraulic presses control the impact pressure for consistent deformation. The ring rolling stage gradually stretches and thins the metal to the desired diameter. Coordination between operators and machines ensures uniform thickness, preventing structural weaknesses. Notching follows, shaping edges for exact dimensions and smooth joining surfaces. Adjustable guides help maintain ring symmetry during rolling. Temperature checks ensure the metal retains proper ductility during rolling. Progressive forging then begins, working both halves of the ring into a consistent round shape. This step includes repeated hammering and adjustments, aligning the metal's grain structure. Each hammer stroke improves the metal's internal cohesion, reinforcing durability for industrial demands. Afterwards, open die forging adjusts thickness and profile as needed. Flat-faced dies guide the stock while hammers fold the metal repeatedly. It's fascinating how the same piece of steel withstands repeated force, yet emerges flawless, ready for the next step. Step forging adds fine details to complex sections. The open die station can handle forgings over 100 tons. Hammer forging targets localized areas, refining shape and density further. Progressive forging continues, completing the round bar form and ensuring consistent dimensions for subsequent applications. The skill required to maintain exact specifications over large sections of steel is remarkable, and misalignment could compromise the entire component. Finally, seamless rolled ring forging finalizes the diameter, producing rings from a few inches to over 30 feet. The metal is squeezed or pounded, balancing thickness and diameter. One misstep in this stage could affect the integrity of 30 feet of steel, showing the importance of planning and teamwork. Rings are cooled slowly to relieve internal stresses. Finished rings are inspected for roundness and surface quality. The coordination among machines and engineers creates a sense of controlled power and craftsmanship, and seeing steel behave this way gives genuine respect for the process. Even after decades of operation, Kilsteel's hammers maintain precise output. Every forging step contributes to the final mechanical properties of the ring and end. Witness the power of the hot rolling line at 1D Auto Parts as steel transforms into semi-trailer axles. Before any processing, the material undergoes a comprehensive inspection. Any defect, from minor inclusions to surface irregularities, is immediately flagged. Operators visually and manually verify markings, thickness, and straightness before cutting to ensure compliance with stringent standards. Once materials pass inspection, tubes are cut to precise lengths using automated bandsaws equipped with adjustable speed and feed settings. Operators program the saws according to tube diameter, wall thickness, and the desired length tolerance. Sensors continuously monitor blade alignment, rotation speed, and vibration, ensuring every cut remains straight and accurate. Watching the tubes glide through the saw with seamless precision is oddly captivating, like steel flowing through a perfectly choreographed system. The tubes are then transported to the hot rolling station. Tubes are heated in high-temperature furnaces to a temperature optimized for ductility and uniformity, then rolled to achieve the exact diameter required. Engineers monitor furnace temperature, roller pressure, and feed speed to prevent warping or uneven surfaces. The glowing steel reshaping under the rollers resembles tiny rivers of molten light flowing through the machinery. Technicians occasionally check manual measurements to ensure the automated system remains accurate. After rolling, tubes are gradually cooled in a controlled environment to maintain structural integrity. Thermocouples attached to each tube record temperature changes, and the system logs every detail digitally. Operators compare the data against specifications to ensure consistency. Hot rolling schedules are adjusted dynamically depending on material thickness and furnace load. Operators inspect the surface finish after each pass to avoid scaling. Minor corrective rolling is applied if slight ovality or deformation is detected. After hot rolling, tube ends are trimmed with high-precision cutting machines to prepare them for bearing installation. Hydraulic presses are used to insert bearings into the tube ends. Calipers and laser measurement devices confirm that each bearing is perfectly seated. Any misaligned bearings are immediately flagged for correction, and operators log each installation for traceability. Hydraulic force and speed are adjusted for bearing type and tube diameter. Each bearing is rotated slightly to verify smooth seating before moving forward. Operators cross-check serial numbers of bearings against tube ID to prevent mismatches. Next, tubes enter the heat treatment stage to harden the steel. Furnaces follow programmed heating and cooling cycles designed to achieve the optimal balance of hardness and toughness. Temperature sensors and timers continuously feed data to the central monitoring system, ensuring that each tube receives the exact treatment. Operators check thermocouple readings and maintain records for every cycle. It's impressive how one furnace can handle dozens of axles at once while maintaining absolute uniformity. Any tube that falls outside the defined specifications is separated for reprocessing. Cooling rates are adjusted based on tube diameter and steel grade. Operators verify the furnace atmosphere to prevent oxidation. Even minor deviations trigger a recheck, showing the strict attention to detail in every step. Logs record every temperature profile for future quality audits. Shot blasting comes next to clean surfaces and create a uniform texture. High-pressure steel beads remove residual scale, rust, or debris from the tubes. Workers inspect each tube after blasting to confirm complete coverage. Shot intensity and angle are adjusted to each tube's surface condition. Tubes are then staged for straightening. Straightening corrects any warping caused by previous processes. Hydraulic and mechanical straighteners apply controlled force, while laser alignment systems verify linearity in real time. Operators manually check each tube post-straightening, ensuring alignment meets the highest standards. Watching a slightly bent tube snap perfectly straight under the machine is oddly satisfying, highlighting the precision of modern engineering. Each tube is logged for quality control before moving to the next stage. Force adjustments are applied depending on tube length and previous warping. Operators mark each tube that requires a second pass for correction. Final straightness is verified with electronic gauge measurement for millimeter precision. Hole boring and end scraping prepares tube ends for axle assembly. CNC-controlled drills bore holes for shafts, and milling machines cut keyways for mechanical connections. Alignment, depth, and diameter are digitally verified. Operators perform random checks across multiple tubes to ensure uniformity. The sequence of perfectly aligned holes across dozens of axles looks almost artistic, with each hole contributing to flawless assembly later. End scraping smooths the tube ends, ensuring perfect mating surfaces for subsequent installation. Tooling wear is monitored and replaced to maintain accuracy. Operators log drill depth and feed rate for each axle. Quality auditors periodically check drilled holes against CAD specifications. Medium-frequency quenching rapidly hardens steel axles. Each axle is heated and cooled according to precise parameters to achieve the desired mechanical properties. Sensors monitor temperature, timing, and cooling speed. It's like giving the steel a controlled shock, and it stiffens perfectly to withstand the loads of heavy-duty semi-trailers. Engineers log each axle's quench cycle, maintaining a digital history of thermal treatment. Any deviation triggers a recheck or adjustment. Cooling media is adjusted for steel grade and tube thickness. Axles are staged to prevent rapid temperature changes affecting neighboring units. Operators check post-quench hardness using portable testers. Outer circle grinding polishes axle surfaces to final diameter. Technicians visually and tactically inspect the rotating axles while grinding. Random sampling confirms diameter, smoothness, and tolerances. Seeing the axles rotate under grinding machines with flawless polish is oddly calming, highlighting the precision behind each product. Properly ground surfaces are critical to ensure subsequent bearing and hub installation functions flawlessly. Grinding parameters are adjusted for axle size and hardness. Technicians remove debris from each machine before starting new batches. Axles are rotated manually to verify concentricity post-grinding. Bushing installation presses bushings into tube ends using hydraulic machinery. Precision alignment tools ensure that each bushing fits perfectly. The consistent power of the hydraulic press ensures a snug fit every time, and observing each bushing slide into place is mesmerizing. Any misfit triggers immediate correction, and the installation is logged digitally for traceability. Alignment jigs are recalibrated at intervals to maintain accuracy. Pressure curves are logged for each press cycle. Operators visually inspect for minor cracks or burrs before moving the tube along. Brake bracket welding secures brake mounting points. Automated welders follow pre-programmed paths, while engineers check each weld for angle, penetration, and integrity. Sparks fly in a dramatic but controlled display. The arcs of welding sparks look like fireworks, emphasizing raw industrial power and precision. Each weld is inspected to prevent cracks or weak points, ensuring reliable braking performance. Torque and alignment of brackets are measured before and after welding. Welds are X-rayed randomly to ensure internal consistency. Operators verify positioning relative to camshaft and hub connections. 6-hole boring prepares wheel attachment points. CNC machines drill the holes with exact alignment and depth, and measurements are logged digitally. Random inspections verify uniformity. The rhythmic drilling across multiple axles creates a satisfying mechanical cadence, highlighting methodical precision. Drill bits are replaced automatically after a set number of cycles. Hole diameters are measured post-drilling with laser micrometers. Axle rotation is checked for concentricity after boring. Camshaft installation positions brake actuation components accurately. Torque-controlled tools verify proper placement and fit. Engineers perform rotation and function tests to ensure performance. The consistent torque application is intriguing, almost like a robotic handshake with the axle. Any misalignment is corrected immediately. Camshaft lubrication is applied before installation to ensure smooth operation. Sensors verify full rotation and movement after installation. Any assembly errors trigger immediate rework alerts. Painting applies protective coatings via automated lines. Cameras monitor full coverage, while technicians measure paint thickness and uniformity. Coatings provide corrosion resistance and durability. Watching paint layer evenly on steel surfaces is oddly satisfying, and the color adds a professional finish to the industrial product. Paint flow rates and nozzle distance are adjusted for axle size. Overspray is captured and recycled to minimize waste. Each axle passes a thickness gauge to confirm uniform coating. In N. Axle assembly integrates all components. Bearings are pressed into hubs, wheel bolts installed, lubrication applied automatically, and brake drums and hubs mounted and aligned. The assembly line functions like a coordinated mechanical puzzle, each operator contributing to the gradual formation of fully functional axles. Torque, alignment, and component fit are verified continuously. N. Each bearing is rotated to ensure smooth engagement with hubs. Lubrication lines are tested for flow and pressure before assembly. Operators visually check brake drum alignment with cams and hubs. Small adjustments are made on the fly to maintain production speed without sacrificing quality. During final axle assembly, tubes, bearings, camshafts, brake parts, and hubs are combined. Engineers perform thorough inspections, torque checks, and alignment verification. Functional load and rotation tests ensure performance standards. It's remarkable how every axle leaving this stage is ready for heavy-duty service, and the scale of production is visually impressive. Axles are tagged with final serial numbers for global traceability. Random stress testing is performed on samples for quality assurance. Final documentation is compiled for each batch before warehousing. Then, completed axles are transferred to warehousing, organized by type, capacity, and production date. Random inspections confirm identification tags, dimensions, and component integrity. Axles are stored systematically for shipment. Rows of completed axles emphasize the factory's efficiency, scale, and attention to detail, ready for distribution worldwide. Every axle leaving 1D Auto Parts is a product of precise engineering and coordinated effort. The factory transforms raw steel into high-performance semi-trailer axles ready for global deployment.
The video captures the entire journey of creating the massive Leehur T282C haul truck, from the early stages of body fabrication to the final assembly. Each steel plate is cut, shaped, and welded under strict quality standards. Every spark from the welding torch adds another piece to this enormous build. Before any transport, all weld seams undergo ultrasonic testing to ensure structural reliability. Workers apply primer and durable industrial coatings that protect the frame against corrosion during mining operations. The sheer size of each component makes even the workshop floor look small by comparison. Standing beside one of the body panels, a person looks almost miniature. Once the body sections and chassis frames are complete, they are prepared for transport from the Port of Brisbane to the assembly site in North Queensland, an incredible 985-kilometer journey. Convoys carrying these parts move slowly through highways, escorted for safety and route clearance. Each transport trip is carefully timed to minimize road disruption. When the components arrive, technicians begin unloading and aligning them on the build pad. Specialized cranes lift the gigantic sections, guiding them into precise positions. Each lift demands coordination and timing down to seconds to avoid misalignment. Assembly begins with welding and securing the main frames, followed by installing the heavy-duty axles, suspension units, and wheel motors. Every connection is double-checked before moving to the next step. The diesel engine and AC drive system are mounted, giving the T282C its unmatched hauling capability. Cabling and hydraulic hoses are organized with care, turning steel structures into a living machine. The entire assembly area hums with focused activity. The cab, packed with electronics and Latronic Plus control modules, is fitted last, connecting the operator directly to the heart of the system. The dump body, hoist cylinders, and payload monitoring systems are attached and tested. It's striking to see how thousands of parts merge into one coordinated structure. After final inspection, technicians run diagnostics to validate braking, drive control, and safety operations. When the giant finally rolls out, its sheer presence commands respect across the mine site. What begins as raw steel ends as one of mining's greatest machines. Each completed truck represents weeks of human effort and mechanical precision, NN.
The double-column machining center operates as a highly versatile and precise tool in various industries such as aerospace, mold processing, and aluminum parts manufacturing. In the case of the CNC Vertical Machining Center CAFO brand double-column VMC 4127, its design incorporates a fixed column bridge type structure with a fixed crossbeam and column and a movable table. The X and Y axes utilize roller-type linear guideways, ensuring smooth and accurate movement, while the Z-axis offers either boxway or linear guideway options depending on the specific requirements of the customer. This machining center can be equipped with different manual attaching heads, such as milling heads, universal heads, extension heads, and multi-directional heads, providing flexibility for diverse machining needs. Key features of this double-column machining center include strong rigidity and low thermal displacement. The design incorporates the shortest spindle center line distance, enhancing rigidity and minimizing thermal displacement during operation. Vibration reduction. The length of the gearbox drive shaft is shortened, effectively reducing vibration for improved machining precision. Balanced weight distribution. The Z-axis is equipped with 2 sets of counterweighted oil cylinders to balance the weight of the spindle head, ensuring stability during machining processes. High-quality linear guideways. The entire machine employs high-quality linear guideways from reputable manufacturers such as Germany's INA or Japan's NSK, THK, guaranteeing smooth and precise movement across all 3 axes. The process of machining a model aluminium engine block utilizing the Hermle C30U machine and a Mugi-Franken high-performance tools involves a comprehensive series of steps. Each step is crucial in shaping the final product with precision and accuracy. Let's explore each stage in more detail. 1. Face milling of cylinder face, roughing. This initial step involves roughing out the cylinder face to remove excess material and establish the basic shape. The Hermle C30U employs a large diameter cutter operating at high speeds to swiftly eliminate surplus material while maintaining dimensional integrity. Two. Roughing of V-contour. Following the roughing of the cylinder face, attention is turned to roughing the V-contour. This process involves strategically removing material to form the V-shaped contour, which is essential for accommodating certain engine components. The roughing pass is executed with precision to ensure the desired shape and dimensions are achieved. 3. Face milling of cylinder face, finishing. After roughing, the cylinder face undergoes finishing milling to refine its surface quality and achieve the final dimensions. A finer cutter is utilized in this stage to meticulously shape the cylinder face, resulting in a smooth and accurately dimensioned surface ready for further machining. 4. Flange roughing. Simultaneously, the flange area of the engine block undergoes roughing to remove excess material and establish the basic shape. This step ensures that the flange area is prepared for subsequent machining operations, guaranteeing proper fit and functionality. 5. Drilling and countersinking of borehole M6. Boreholes for M6 screws are precisely drilled and countersunk to accommodate fasteners securely. The Hermle C30U employs advanced drilling techniques to ensure accurate hole placement and alignment, essential for the assembly process. Six. Cold forming of threads M6. Threads for M6 screws are cold formed to provide durable and precise threading, ensuring secure fastening of components. This process is carried out with meticulous attention to detail to guarantee the integrity and strength of the threads. Seven. Finishing of V-contour for M8. The V-contour for M8 screws undergoes finishing to achieve the final dimensions and surface quality. 8. Roughing of borehole M36 by 1.5. Larger boreholes for M36 screws are roughed out to prepare them for finishing operations. This step involves removing excess material to establish the basic shape and dimensions of the boreholes, ensuring they are ready for subsequent machining processes. Nine. Drilling and countersinking of borehole M8. Boreholes for M8 screws are accurately drilled and countersunk to accommodate fasteners securely. Precision drilling techniques are employed to ensure proper alignment and fitment of components, crucial for the assembly process. Cold forming of M8 threads. Threads for M8 screws are cold formed to provide durable and precise threading, ensuring secure fastening of components. This process is executed with precision to maintain thread integrity and strength. Finishing of borehole M36 by 1.5. The boreholes for M36 screws undergo finishing passes to achieve the final dimensions and surface quality required. This step ensures proper fitting and alignment of components, contributing to the overall functionality and performance of the engine block. Finishing of housing. The housing of the engine block undergoes meticulous finishing to achieve precise dimensions and surface quality. This ensures that the housing is ready for assembly and can accommodate all necessary components securely. Pocket milling. Pocket milling is performed to create recesses or pockets in the engine block as required for specific components or features. This process is carried out with precision to ensure the accuracy and integrity of the pockets. 14. Thread milling M36 by 1.5. Threads for M36 screws are milled to precise specifications, ensuring proper fitment and secure fastening of components. This step is crucial for the assembly process, as it ensures that all threaded connections are robust and reliable. (15) Flange finishing. The flange area undergoes meticulous finishing to achieve the final dimensions and surface quality required for proper sealing and assembly. This step ensures that the flange area is smooth and free from imperfections, allowing for secure attachment of other components. 16. Fanning of borehole M36 by 1.5. The boreholes for M36 screws are fanned out to ensure proper alignment and fitment of components. This step is essential for ensuring that all components are securely attached and aligned, contributing to the overall integrity and functionality of the engine block. Throughout the machining process, the Hermle C30U operates at high spindle speeds of 18,000 revolutions per minute, powered by a robust 15 kilowatt spindle with a torque of 130 Newton meters.
Every engine carries a signature of its creator, and at Mercedes-AMG, that signature is literal. In the case of the M139 2.0-L 4-cylinder engine, each unit is built by a single technician under the one-man, one-engine philosophy. The raw aluminum blocks arrive at the AMG facility, their surfaces shining under factory lights awaiting transformation. The first step involves thorough cleaning, visual inspection, and removal of any surface imperfections. Every millimeter counts when building an engine capable of producing 421 horsepower. It's impressive how these seemingly simple blocks can host such complex machinery. Operators often pause to ensure that each block meets exact AMG tolerances before proceeding. Next, the crankshaft is installed. Each crankshaft undergoes hand inspection for balance and smooth rotation before being fitted into the engine block. Specialized tools measure micro vibrations in the crankshaft to ensure performance reliability. Connecting rods and pistons are carefully assembled, lubricated, and lowered into place. Operators apply specialized oils to ensure friction-free movement during initial rotation. Tiny variations in alignment can impact engine output, which makes this process surprisingly intense. Cylinder heads are mounted, valves inserted, camshafts aligned, and timing chains fitted. Technicians work in sequence to guarantee that each moving part interacts flawlessly with others. Each camshaft is rotated manually to verify smooth operation before securing. Turbocharging and intake systems follow. The turbocharger is bolted onto the engine, and the intake manifold is positioned to direct airflow optimally. Sensors and wiring harnesses are installed to monitor critical parameters, ensuring peak performance. Fuel injectors and ignition systems are calibrated with precision, so combustion occurs at the perfect timing for maximum efficiency. Ingots. It's funny to think that the tiniest misalignment could reduce this engine's 0 to 100 kilometers per hour time. Every bolt is torqued to AMG specifications, and hoses are routed carefully to avoid interference with moving parts. Technicians periodically inspect torque values twice to ensure they haven't shifted. During assembly, technicians frequently double-check measurements, clearances, and torque values. Each step combines human skill with mechanical aids like jigs, torque wrenches, and laser alignment tools. AMG's dedication to blending technology and craftsmanship ensures that every M139 engine meets exacting standards. Even auxiliary components like sensors and brackets are verified for correct orientation. Once assembled, engines are tested on AMG's dynamometer test benches. RPMs, torque curves, emissions, and vibration are all measured in real time. Engines are run through multiple cycles, simulating driving conditions, from city streets to racetracks. Data from each test cycle is stored for future reference and quality tracking. After testing, engines undergo final inspection. The technician who built each engine signs it personally, engraving their name on the engine cover. Engines are then fitted with protective covers, packaged carefully, and prepared for shipment to assembly plants worldwide. Even minor shocks or temperature fluctuations during transport are considered, reflecting AMG's attention to detail. Each crate carries the assurance that one individual's craftsmanship will reach customers intact. Throughout the facility, the synergy between human skill and automated tools is evident. Conveyor belts move engine components efficiently, but hands-on expertise guides alignment, torque, and calibration. Watching a single technician assemble an entire engine highlights the value of experience, patience, and focus. Every step, from the first bolt to the final inspection, is critical to achieving the performance numbers AMG promises. The 421 horsepower engine and its 500 Nm torque allow the A45S4 Matic Plus to sprint from 0 to 100 km per hour in just 3.9 seconds. AMG's production philosophy emphasizes accountability, skill, and precision. Operators frequently cross-check each other's work, ensuring nothing is overlooked. Tiny components, from seals to fasteners, contribute to overall reliability and safety. The M139 engine embodies hundreds of hours of design, engineering, and craftsmanship compressed into a compact, high-output package. Every finished engine represents a collaboration of technology and the individual's dedication. Even packaging is inspected to ensure no moisture or dust compromises the engine. Finally, engines are shipped to assembly plants where they will power A45S vehicles worldwide. Even logistics involve careful planning to maintain engine integrity. Each crate is labeled, handled, and transported to ensure zero damage. AMG's combination of human precision, innovative machinery, and systematic quality control results in engines that consistently deliver on performance and reliability. It's surprisingly heartwarming to think that one person's work can define the driving experience of countless vehicles. The One Man, One Engine program demonstrates how focused skill, passion, and high-tech support merge. Each M139 engine reflects the sum of hundreds of small, precise actions, coordinated to produce an extraordinary driving experience. It's amusing that the result, a roaring 421 horsepower engine, is simultaneously a work of art and a tool of pure performance. AMG proves that human craftsmanship and advanced technology can coexist, producing engines that are both mechanically flawless and emotionally satisfying. Every engine passes final calibration tests before leaving the facility. Each stage at Toyota's Motomachi plant reveals the careful integration of the Mirai's chassis and fuel cell system. The facility, once known for building the LFA supercar, now focuses on producing the Mirai, a hydrogen-powered sedan that represents Toyota's commitment to a cleaner future. Each movement in this line feels like a quiet statement of progress. And now, the process begins as the CFRP, carbon fiber reinforced plastic, stack frame takes its place at the assembly area. This lightweight yet incredibly strong structure supports the core components of the Mirai's hydrogen system. Workers align it with exact positioning tools to ensure every bolt connects seamlessly. You can sense how every part seems designed to fit with absolute purpose. Once the frame is secured, the fuel cell stack, the heart of the Mirai, is positioned and installed. It's here that hydrogen and oxygen will later generate electricity to power the car. Following this, technicians attach the boost converter, hydrogen tank, and intricate tube network. That web of silver lines almost looks like veins carrying life into the machine. A helium-based hydrogen leak test then confirms the system's airtight integrity, ensuring no gas escapes. The attention to safety is unmistakable. After validation, the fuel cell stack and hydrogen tank are mounted simultaneously, streamlining assembly and balancing the vehicle's layout. This synchronized installation shows how planning meets practical design. Next, the electric motor is prepared, followed by the marriage of the air compressor to the stack, a critical pairing that supplies air for the electrochemical reaction. Then come the drive shaft, front axle, inverter, water heating unit, and high-voltage cables. It's wild to see how many systems intertwine in such limited space. Finally, the front suspension, rear axle, bumper, and wheels complete the chassis build. By the end, what began as a bare structure now stands as a nearly complete hydrogen vehicle, ready for final testing. The quiet power behind this process feels futuristic, yet grounded in craftsmanship.